All right. So we're going to talk about dimension reduction using principal component analysis. I'm going to do my best, but this is still something new to me. So if y'all have questions, maybe we can work it out together. So we're going to do a
Wait,
broad overview.
just a
Yes.
question. So you're going to start with principal component and then go to KDE?
I guess I'm not sure if I'm going to go to KDE. Like I didn't, because Kevin suggested maybe we just not. I mean, we
Okay.
can, but I, what do
Okay,
you?
so yeah, let's see where we're at the end of this.
Okay. Um, this is the outline. We'll do our best. So basically, this is an example of getting some medical data. So Ban, you might like this. They're getting a bunch of like blood and urine samples. They're measuring a lot of stuff. You get this big matrix, and there's a lot of features. And because you have so many features, it's challenging to see the correlations between them. So is there a better way to represent this than just like 53 different coordinate axes? Do we need all 53 dimensions? Can we do some type of subspace that captures the most information, right? And this is the idea behind dimension reduction. So we're going to take these 53 different features and squish it into something that maybe is a little more useful, that gets like the most information, but just in much less data. This is an example. I'm not exactly sure what's going on here. Um, so we're gonna keep going. So what is dimension reduction? Basically, we want to take information represented, I guess, here with this vector r with to the raised to the d. And so we have this original data, and then we're going to do some type of reduction function that's going to allow us to represent it with less points, right? Where k is much less than d. And basically, we can do this by transforming, combining different variables. I think it's going to make a little more sense as we keep going. So this is useful for if you just want to understand data. So you might be an experimentalist working with medical data and you need to better understand it. You might want to aggregate the weak signals, clean it up. This is a lot of like use cases for reducing high dimensional data. And the key questions here listed on the slide are: what is the criterion for carrying out the reduction process, and what are the algorithmic steps? So this is now going to lead us into principal component analysis. Are there any questions before I move on?
What did you skip over?
Yeah, I don't know, because like there's not a lot of. I mean, we can try and imagine what this might be trying to
I
say.
see. Okay, what's the
I
next
mean,
slide?
it's literally just trying to say like, just looking at it, you wouldn't have a clear like you won't necessarily know what the relationship is between data points, and so it's just saying like, okay, look, you can visually look at like the bottom left hand corner. You got three clusters. You kind of see how they're clustered together, but you don't actually know what the relationship is between the different clusters. Same with like the rings and like the other data points. You can see that they have some sort of distribution together and they've clustered themselves together, but you don't really know what the like what's the relationship between these two like blocks of data, right?
Hmm. And okay, I guess this is just another example of that. Um, Maybe you're trying to find the relationship between these two documents. So
Okay.
we have another one here.
Yeah. So it's like you don't like you're trying to find out what the relationship is between all of these like different features, right? You have like a database, you have SQL, you have index, regression, likelihood, linear, and you have all these instances of those things, and you don't know how any of these instances relate to other instances or how any of these features uh, relate to each other. Where, like I don't know, how do you know like what database is how that relates to like regression or something like that?
Hmm.
Okay.
Um, this is another example that I'm not exactly sure what's going on here because it's
Okay.
pretty sparse.
Yeah.
But my understanding is that we're taking higher dimensional shapes and, potentially projecting it into lower dimensions. So he drew this shape here, which I think gets to the concept of PCA a little bit, by looking at the best projection of these weird shapes. But I mean, really, it's hard to know what he meant here without him explaining it. Like, if you are able to make this jump, be my guest. But,
Yeah, I see what you're saying. Yeah.
Yeah. Exactly. So, so this is a pretty good example of kind of what's happening mathematically and conceptually. Although I would argue that with the classification of good and crappy wine, I probably wouldn't use PCA. I might use a linear. There's another word for this, but let's come back to this. Maybe we can.
The second link I sent is actually about wine.
Yeah, exactly. And so I figured, yeah, that one's really good. But I just feel like this jumps in and skips so much. So let's start here. So, one way to reduce dimensions is to capture variation. And this makes sense because, as we learned last lecture, variation is like a stand-in for entropy in some ways. And the higher the entropy, the more knowledge or the more information is captured. So if we look at if we try and capture the variation in our data set, we're trying to capture as much information in as little dimensions as possible. So, we can look for signals, information in the data, but, there's things we need to do before we can, directly use it. So we need to normalize. And by doing this process, this kind of gets to what the second part, the part I skipped over, is that we can actually start to see how some of these dimensions are related. So it's going to make a little more sense as we keep going. But are there questions here?
No.
Okay, so let's take an example. So we might have some data set, and we're going to look at two of the features and plot them on this 2D map. And so we have, right, as we have feature 1 going from -4 to 6, feature 2, and you can see that this has been, I guess something's been pointed out here. We can see that the direction of these, I guess we can see the variation in each direction, right? And so if you compare this direction to this one, we see there's more variation because this line is longer, right? There's more variation in this direction as opposed to in this direction, there's less variation. But we can also see that these features are correlated. So you see this, it has a shape, right? It's not like we have these data points that have no correlation at all. I think one thing I want to bring your attention to is that these lines are perpendicular to one another. So theoretically, you could represent this data set by rotating it, and then you actually would get rid of that correlation. So if you took this X, I guess this line and this line, and you rotated it such that this is the X dimension and this is the Y, now you're looking at a different coordinate plane where the features are no longer correlated, right?
Yeah, fully independent.
They're fully independent. So let's keep talking about this because we'll come back to that point, I believe. Here we go. So principal component analysis does two things. One is going to maximize the variance of the projected line. So we're going to pick some line such that the variance is maximized. This is the purple line. And then additionally, we're going to minimize the mean squared distance between the data point. Notice that this is a little different than this is an orthogonal regression as opposed to a simple linear regression. Because you can see these lines are have diagonals, right? Typically when you do a linear regression, you're either choosing the X or the Y. And so these lines would either be horizontal or vertical. But when we do an orthogonal regression, we are able to minimize the mean squared distance between the line and all the points without having to choose an orientation. Does that make sense? And Bayon posted this really nice thing I'm going to go to where we can see how these both happen at the same time. So let's say this is basically our regression line, right? And the red lines represent the error.
The mean squared, yeah, the mean squared distance.
Square distance, or I guess the error in between our like regression line and the actual points. And you can look at the point when the error becomes minimized. So that's when it actually lines up with these purple points. And then you can also look at the variance, right? So the variance is the distance between these red dots. So you can see like here, right, the variance is minimized, but remember, we're trying to maximize the variance to capture as much information. That also happens when the line matches up with the purple lines. So even though it seems like they're different, it's actually the same thing. So maximizing the variance and minimizing the mean squared distance is the same thing, right? And we do that by making this line called an orthogonal regression. This, I imagine, would have been animated, but I showed you the animation, so we're gonna keep it pushing. So that's the main idea between principal component analysis. What we're gonna do is we're going to look at these features. We're going to draw basically some form of regression between the features that's gonna capture as much of the variance as possible while minimizing the mean squared distance. And we're gonna say that this is gonna be useful for us in determining what are going to be known as the principal components of our data. Any questions here?
Nope.
No, sir?
No, that makes sense.
Okay. Okay, here's our variance equation. All right. So we formulate the problem first by looking at the mean as well as this norm. I think this is like a 2 norm. Is that the word for it? And we're considering the norm such that it's equal to 1. The idea here is that I guess geometrically what we're doing is we're centering our data with the mean. Well, we'll get to that next. But we need the mean and the norm. So given the data points, n data points of x1 all the way to n of dimension d, and we have some mean mu as well as some normalized w such that it's constrained to equal 1. What we want to do is we want to maximize, let's see, such that the variance of the data along direction w is maximized using this equation, where this is going to represent the variance in the new feature space. So this is an example of where the math is just beyond me. I don't.
So the reason why you have the norm of w normalized to be 1 is because we don't actually care about the amplitude of w. We actually want the amplitude of w to be 1 so that it's sort of exactly the same. Like you're not changing the data at all. You're not amplifying or de-amplifying the data, but you actually care about the direction of w. And so that direction is going to correlate with the that like principal component or like orthogonal line to like all the data that you talked about earlier. So that's kind of what w is. And then so this is just saying that you have the variance inside the sum. Remember we talked about variance has always been being the data minus, so if you just don't look at the w right now and just look at xi and w and mu, so it's the difference between each point minus the mean squared, and so that's just the variance there. And so you're trying to maximize that such that the norm is equal to 1. So that's like a constraint that you have on this equation, so that you don't change the data at all. You don't scale the data at all, but you're just getting the direction.
So w is just some unit vector that's arbitrary.
Exactly. exactly. And the unit vector that you're trying to find is that line where you're going to have the maximum of the, I guess, data minimum squared, whatever, mean or whatever.
And what does the omega stand for?
Omega. Oh, I think that should be W.
This should be
I think
W.
you screwed that up. That should be W as well. Yeah, it seems like that should be W because that's how you calculate. Yeah, that's how you calculate the norm. Is you. Yeah, so I think it should be W. That's just like a mistake. Typo.
Okay, so I guess the variance in this new feature space is this variance equation multiplied by the direction, the unit vector W. And we're maximizing it such that the variance, we're maximizing the variance in the new feature space, right, to capture as much information. And so with this slide just shows us, we can think, to maximize it, this becomes an optimization problem. And so,
sorry, let me just round up by, yeah, so right here. So this equation, how you would read this kind of equation is find W that maximizes this equation inside the max such that W or the norm of W is equal to 1. So that's what this says in like sort of words.
okay.
Yeah.
Okay, I see. So this shows you how they're going to, because what we're going to find, well, let me just take you through. So we start with this equation, and then there's going to be some steps where they pull out the W, and then showing that, like, I guess this is true, like the A transpose times A is the squared version. So they basically take this and they're going to say this transpose times this, if this is A, right? We can break this out. And then they use another linear algebra rule so that like AB transpose is the same as B transpose times A transpose. So if you consider this to be A and B, then you can further disaggregate this by saying W transpose, right? This was B, times, this is our A transpose, right? So we broke this apart, and then we're going to distribute the W to, did we distribute that? No, not yet. Leave it like this. Okay, right? So we took this part, we broke it out, so now we have 3 terms in here. And then there's going to be one more step. So they pull the W transpose out of the summation. And
yeah, you can do that because the sum is just over the xi's. So you don't, W is basically a constant here.
I see. Okay. And then what they do is by pulling out this W transpose, we can look at this and say, oh, I remember from my linear algebra class, this is just the covariance matrix. And so they replace it with C, where C represents the covariance matrix. So we have W transpose C times W, which is interesting. And I think next slide talks about it next. But do we follow that math somewhat?
Yeah.
This is the key part. You just need to trust that, I guess.
Well, that's true. This is a fact. That's the covariance matrix.
Could we go back up for a sec? Is so xi minus mu is representing the mean, right?
Yeah.
Okay, so it's just each data point minus the mean. Okay.
The mean
so,
of all the
okay,
data
I
points.
see it. Huh?
The mean of all the data points, right?
Right. Yeah.
Collected. Yeah.
Yeah. Okay, that makes sense. Okay, so that's how it's okay, I see how you get the covariance matrix.
Okay, so we're claiming that the way to maximize this such that, well, we're saying that basically we rewrote this problem, and now we're reframing it to say we want to maximize W such that the norm equals 1, or maximize this function W transpose times the covariance matrix times W, such that the norm of W equals 1. All right. And so what they're going to do is they're going to do a Lagrangian function to do the optimization. I guess you also need to be familiar with using Lagrangian in order to optimize, or I guess find your maximum or minimum. In this case, we're finding the maximum. And we're going to say that we're going to stick on this term because that's how you do it. I've never seen this. So like what class do they even teach you Lagrangian optimization?
I've learned it. I've seen it in several classes, and some of them are linear algebra classes because it's a common thing in the algebra.
I picked it up in a few of them were optimization classes. I first saw it in a quantum mechanics class for electrical engineers.
So I did talk about this last week, but I didn't go through it. Maybe I should have went through it because that would have been more. Yeah, that might have been more helpful. But basically, the Lagrangian just takes two functions. So you construct it basically using two functions. F of x, which is the first thing here, or I guess in this case, f of w, which is your the objective function, and then the g of x, or g of w in this case, is your constraint function. So basically what you do is you say, okay, my constraint function, this w norm, it's just w transpose w. I don't know why he's like messing up the notation here. This should be like a capital T up here. So it should be w transpose w, and that's how you calculate the norm. And so you basically can write the equation as that constraint equation as w transpose w equals 1, right?
Fuck. Let me put my mouse in. All right.
Right. And then basically you just want to like set it equal to 0. So you just bring the w transpose w to the other side and set it equal to 0, and that is your constraint equation.
Where did he pick up w transpose w from? That's
just what the norm is defined as.
Oh, it's the norm. Okay.
So yeah, in this case we take the 2 norm.
Let me erase this and try this.
Yeah, that makes sense, because I learned it as the objective function plus lambda times the g of x
equation.
Function.
Yeah.
Okay, so we set this equal to 0.
Yeah.
Right.
But like here you could do that function that you just wrote, or you can multiply by -1 and still be the same equation, right?
Okay.
And then you just tack on the Lagrange coefficient to that.
Okay, so this is our objective, and this is our you said g of x, but
yeah, constraint equation.
Yeah, constraint equation.
Okay.
So the Lagrangian method allows you to optimize some objective function given, it allows you to do constrained optimization. So you have a constraint and you have an objective, and you're trying to optimize the objective such that the constraint is satisfied.
Okay.
And so the way you solve it is, how you solve any other maximization or minimization problem is by taking the derivative with respect to the variable you're trying to maximize or minimize.
Okay, so here we want to minimize w, right? Then can you walk us through what this means here?
W is the maximum of the original optimization problem. Then there exists a lambda where lambda is a stationary point of. Yeah. So.
Point of no change, right?
Yeah. So I mean, it's saying that. I think it's saying that if this equation is to hold, and the
Wait. Hold up. It went, gargoyle-y. Can you? Yeah. Hello?
Can you hear me?
Yeah.
Okay. So I think it's saying that it's basically saying there is some lambda. Like if this equation has a maximum, right?
Okay.
There is some lambda where this w or these 2 points, like some w that you find and some lambda is like you can like you can basically graph a point of this w lambda, right? I mean, I don't really know what stationary point per se means, but I think it just means that there's some lambda such that this function is maximized.
Yeah, it's like an inflection point, right?
Yeah. Okay,
It basically
stationary
is.
point. Yeah, because it's a derivative. Yeah. So stationary point, I guess it means because when you take the derivative of a point that is a
It's at the
maximum,
max. The
the
the rate of change is 0.
yeah, the rate of change is 0.
So what it's saying is like you've hit the peak. You're at the if you think of like a concave. Yeah,
Yes.
concave
So the
function.
derivative at that point is 0.
Right. And so that's the point of it. And that would represent an inflection point where if you went to the left or to the right, you immediately start increasing or your slope starts to change.
So basically, it's fancy words for saying we can do a derivative to use it to find the maximum point.
Yeah.
We're by setting it equal to 0.
Yeah.
Okay. I think that's certainly a little more familiar. So we're going to do the derivative of the Lagrangian, set it equal this Lagrangian optimization function, set it equal to 0, and then because the W transpose W equals W squared, so we can think of this like that. I think he wrote it here. And so when you do the derivative of this, it's just 2W, right? So we have 3 terms. We have this term. We'll have the lambda. Then we're going to have minus W squared. And this simplifies to 2 times the covariance matrix W minus 2 lambda W. And those 2's drop out. We end up with the covariance times W equals lambda times W. All right. Thank you all for contributing to the, let's see, math.
Okay, so this is just saying that equation is just the eigenvalue problem. So you can recognize it as the eigenvalue problem, right?
So it's just telling you that solution we just the derivative of the Lagrangian returns you that function CW equals lambda W. So now you can determine what the lambda is to get the eigenvector, which tells you that's like
that's your principal component. Or helps you get your principal component.
Well, okay.
It's a principal component. It's the eigenvector of a singular principal component feature. Not all of them. It's just for the one. So the entire matrix of features will give you a lambda will basically tell you a lambda of a singular feature tells you the importance of that feature related to all the other features. So that'll, and then the eigenvalue or the eigenvector is the, okay, I just know that the lambda is important. It tells you
Stuart,
that.
do you know what the eigenvalue problem is, right?
No.
Okay. So that's basically what they're stating here in these first 3 bullets. It's saying that this is the eigenvalue problem. So given a matrix C, it could be A, it could be B, whatever. I think it's usually written as AX equals lambda X or something like that.
Yeah.
I see. Okay, go ahead.
Yeah. So exactly. So in this case, we're actually going to add a sort of an additional constraint to our x in that ax equals lambda x problem. But so I'm just going to now say ax or a is equal to c and x is equal to w, right? So we're going to add an additional constraint that w is normalized, that we make sure that the norm of w is equal to 1. Exactly.
Okay.
And that's it. Yeah. And so then we can, so he just states the eigenvalue problem here, and now he's gonna and with this additional constraint that w is normalized, and then and then he goes on, I guess.
Right. So this is what I was referring to. Each of those lambdas are representing the importance of the magnitude of each principal component feature. So each column, independent variable column. And so you'll end up getting a solution that has lambda 1 through lambda d. And those will represent how important each feature is and its respective vector. But you'll see it like as we go down.
Yeah, I think so. So here we go. So we've done the algorithm. Basically,
we haven't done the algorithm yet.
Right. Well, we haven't done the algorithm yet, right? But like this gives us a way to determine essentially our unit vector w such that we've maximized the variance and minimized the error. So let's look at this again. So what we do is we say principal direction w satisfies it such that the covariance times w is going to be equal to w times lambda, and where lambda is the eigenvalue.
Okay. Yeah. Okay. So let me help. So if you scroll up, all the way up to this maximization problem. So we started with here. Yeah. Oh no, down a little bit. Yeah, here. So we started here, right? We started saying that like we want to maximize this function given this constraint, and it turned out that what the equation that we get that maximizes this function is this CW equals lambda W, right?
Yeah.
And so what we're going to kind of see from here, and it'll be shown in the next few slides, is that so go back up a little bit. So if you look at this equation, CW equals lambda W, and you plug it back in to the that maximization function
here.
Yeah. So if you said that the W you found had to be normalized by 1, so how do I? Yeah. So if I'm looking at this down equation, CW equals lambda W. Okay. And now if I want to find because this maximum is going to be like an actual scalar value, right? So if I want to find the actual scalar value that is going to matter, I know that if I just take the norm basically of this equation, the CW equals lambda W, I'm going to get the scalar value. So if I take the norm of CW, I know that the norm of W is 1. And so I just have basically the norm of C. And on the other side, I have norm W is 1, and so the lambda just remains there. So what ends up happening, or actually an easier way to see this is, an easier way to see this is if I multiply. So I have CW equals.
Sorry. Here we go.
Can you still hear me?
Yep.
Okay, so I have CW equals lambda W, right? I can move, because lambda is a scalar, I can move it anywhere. So I just move it to the outside, let's say. And so now I have CW equals W lambda.
Okay.
So now I can multiply both sides of this equation by transpose.
But you're back. Okay, try it again. Try again.
So if I multiply both sides of this equation by W transpose,
Right.
now I have W transpose C. Oh,
That's what's happening here.
So now I have this, right? So I have W transpose CW equals W transpose W times lambda. And we know that the norm of W, which is equal to W transpose W, is 1. And so that tells you that so W transpose C times W is going to be equal to lambda. And so the function that's going to, or the value of lambda that's going to maximize that that function that we originally started at has to be the highest value of lambda that we find.
Right.
Highest value of lambda that we find.
Yeah. So assuming there's a way to solve for lambda, assuming there's a way to find lambda, we know that what's going to maximize WTC times W is going to be the highest lambda we find.
Like the largest magnitude of lambda.
Largest magnitude.
Yeah. Okay. Maybe this will make more sense. Maybe we can come back because like conceptually PCA makes sense. So, but
I mean, what doesn't make sense about the math? I guess.
Well, there's some connection here where it's like we're going to find the maximum eigenvalue, lambda, to maximize this. And it's like maximum eigenvalue of what?
Of CW equals lambda W.
Right.
So that's an eigenvalue equation that you can solve and find all the eigenvalues, right?
I see.
So you solve that equation, you find eigenvalue 1, eigenvalue 2, eigenvalue 3, eigenvalue 4. And what we're saying is that whichever one is the highest one of those is what's going to maximize the maximum objective function.
Okay. Yeah. Did you see how like if you wanted to find a scalar for this, like a scalar for that the maximization problem at the top, that we're just plugging in lambda W for CW, and then it's like we're basically just like taking things that we already know, constraints that we already know, and it eventually boils down to that the max of our original objective function will be this lambda.
Right, but like I get that. I think really what happened here, because wasn't that we could have done that from here, right? I think what happened here is we're putting it into a form that now we have like linear algebra tools to bust out this eigenvector, these eigenvalues, and then look at the highest values, right? Like I think what here was a form change as opposed to gaining some insight into how this works. Does that make sense? Like,
well, but this is kind of the crux of it, right? Because this is saying that the principal direction has to because we started with the problem of like solving this maximization function. We're saying that this is actually how you will get that maximum value. It has to be the highest eigenvalue. Yeah. And so we know that when we solve this eigenvalue problem, for each one of the eigenvalues, we also have an eigenvector, right?
Right.
And so then it says this principal direction W is going to be the eigenvector, so that's a vector with some direction that corresponds to the largest eigenvalue.
How do the eigenvalues relate? Because I guess my linear algebra is not strong.
Wait, Dan, what's the question?
Sorry.
How do the eigenvalues relate to the eigenvectors?
Okay, yeah. So for each eigenvalue you find, do you remember that you also find a corresponding eigenvector, or you don't remember that?
Well, I know that that's true, but I don't understand the mechanics of that.
Oh, okay. but so you know how to you know how to calculate them though, right?
No.
Oh, I
You
see.
do like the determinant of a minus lambda I,
Yeah,
the
you should
identity
do
matrix.
assignment one. Assignment one will have you calculate them.
Okay.
Yeah.
Let's keep it pushing. Bam, were you going to say something?
Yeah, if you go back up to that spread, the graph of data, yeah, this. So the thing is, like, we don't actually know what direction lambda or omega, like this W is, right? So, like here, they just put up a direction, which maps to the direction the spread of like the direction that the data seems to be correlated towards. So what we're doing is when we get all of our eigenvalues, each eigenvalue is like a magnitude, and its respective eigenvector are just direction vectors. So the one that has the largest magnitude will tell you that this is the direction of the maximum variance, which is what we're trying to do. So it just tells you this is the most, like this is the direction that the data goes.
I,
Does that make sense?
The direction
I,
of the maximum variance, because
the,
that's how we started.
right,
What we-
and that captures the most information. So I guess let's keep going, and then let's ask questions.
Okay.
So basically, by doing this math, which I don't understand yet, but what happens is we'll get these W1, W2 that have the largest variance but are still orthogonal to each other. So these are independent vectors, I guess. And these, so take eigenvectors W1, W2 of C, corresponding to the largest eigenvalue lambda 1, second largest eigenvalue lambda 2, and so on. So basically what happens is we're ordering those eigenvalues in terms of greatest to least, greatest to least, and the corresponding eigenvectors to each of these eigenvalues maps onto these W1, W2, which we call our principal components, right? So because W1 has the most variance, based on information theory, we know that this eigenvector carries the most information about our data set. So let's look at this. Oh, and then also they're orthogonal to each other, which is important. So now we've taken our data set. We're just looking at 2 features, right? But this could be 2 features of 53 features, like from the beginning. And we're saying that W1 gives us a principal component of our data set, right? Even though it's made up of, in this case, 2 features, it could be made up of more. But this feature, this artificial feature we're creating, right, this W1, which captures the most variation, allows us to get a principal component that captures the most information with little, I guess, into one feature. So I think actually now might be a good time to go back to, well, let me see what comes next, and then I might go back to the wine example. Yeah, so principal component 1 points in the direction of the largest variance. And each of the subsequent principal components is orthogonal and points in the direction of the largest variance of the residual subspace. So let's say we take out, we use eigenvector 1, and that's going to give us our principal component 1, right? And then we might have some orthogonal principal component 2, and that is going to be the largest variance in the remaining subspace. So let's go to the wine example. I think now is a good time. All right. So what we might do, another way to think of it is we might have, now we're taking this, we're making it a little more real. We have wine, right? And these 2 features of it are the price and the age, but realistically, we probably also have the smell, the color, the region it came from, right? The grape. And additionally, we know that a lot of those features are correlated to one another. So if you just look at here, the age and the price, we can see the correlation. And so it might not be enough just to take one feature and say, I'm going to use this to determine the goodness of my wine. It might be better to say, well, is there a way to somehow map, right, I guess, pull out the principal components, and these principal components might actually be made up of multiple features, but we're taking it in a way such that now we have principal components that are no longer correlated. These are independent features that we're creating from the data set. So here we see that we drew our orthogonal line, or we did our orthogonal regression where we're maximizing the variance. And essentially what we're doing is we're rotating it to the z-axis, where z represents our, I guess, principal component axis. That's the direction W. And we can see that z is actually comprised of multiple features. In this scenario, it's comprised of, oh wait, am I making sure, do I understand this right?
Yeah, it sounds like you're, yeah.
Oh, okay, yeah.
It's some linear combination of those features.
Some linear combination of those features weighted by this, I guess, W direction. Yeah. And so we can, yeah, basically we get this principal component that is weighted by whatever what this is going to be. Am I doing this right? Or did he do it right? Yeah, this is, we're taking the eigenvector and multiplying it by the remaining data points in order to get this principal component Z1, where the J value represents eigenvector 1. I think that makes sense.
Yeah.
And then when you sum up, well, I actually don't understand that all that well. But essentially what it allows us to do is it takes these multiple dimensions. In this scenario, we had 2. And by putting it onto Z, so that's what it looks like here, we've mapped it into 1 dimension. So we've crunched those. I think in here they take the 2 things and they map it onto age, but really what's happening is that we're taking these 2 dimensions and crunching it into 1 on the z-axis. That's the dimension reduction that we started talking about.
Yeah.
Okay, so we were here. So now let's talk about the algorithm. I guess, are there any questions about what's happening conceptually? Okay, so in order to do this, there's 2 steps, right? You find the mean. Well, there's many steps, but step 1 includes finding the mean, and then you also compute the covariance matrix from the data. Then what you're going to do is you're going to take the eigenvectors of your covariance matrix that corresponds to the largest eigenvalues, right? So each eigenvector, as you remember, is a principal component, and they represent from greatest to least the amount of information that we can pull out, or the amount of information we can pull out from the data set. I'm not sure if I described that well, but hopefully these are our principal components. And then we're going to compute the reduced representation. So what we can do is we've computed these W's, and these eigenvectors we're going to use as weights, right, to, I guess, have our reduced representation. So we can actually choose, the number of weights we want to use to represent our data set. And so what we're doing is K represents the number of weights. And so we're taking our D-dimensional data space and we want to say, you know what? I actually think that I can represent my 53 blood and urine samples with just 5. And so I'm going to use PCA. I'm going to say my K is equal to 5. So I'm reducing it from 53 to 5. And I'm going to take the 5 principal components and sum those up. So I get a reduced representation version of my 53 dimension data set. Does that make sense?
Right. And all of the data that you all of the other dimensions that you decided to not use still have some residual information that gets pulled into the first 5 that you used as a result of you looking at variances.
Well, each principal component is going to have information from all the dimensions, right?
So that's why it's fine. But
it's just a matter of how much information are we capturing. And there's ways to decide, like your K, it's a little bit of an art is what I'm reading. So one thing that is going to come up is like, okay, well, how do you get, right? You need to, step 1 is, you get your covariance matrix, your mean, and then you need to compute the eigenvectors. And that can be an issue if you have a really large data set. So the technique people use is they use singular value decomposition, which is an efficient way to pull out our, I guess, these matrices. Again, I'm not very super comfortable with the math, but what's happening here is we're saying that according to PCA, we need to get, we need this equation. And so we're going to exploit singular value decomposition in order to compute our covariance matrix quickly and efficiently. Maybe y'all can walk through the math. I can't. But
all they're doing is normalizing. Like they're just normalizing so that all data points are centered around the mean of 0, I think.
Well, they center it and then they normalize it. So they center it such that I guess that accounts for, I think the word, if you think of it.
Well, that's how you generate the covariance matrix, right?
Yeah. Okay.
Yeah. So I think they're just defining this big X here by showing you that this xi minus mu is what you're defining as big X.
Oh, I see.
And then taking big X and finding the singular value decomposition of it gives you this mu sigma whatever. And then you know that the X transpose X you can just write as this big thing here. And then using some properties of the singular value matrices that they're orthonormal, basically meaning that this U transpose U is going to be identity matrix, right? And then this sigma transpose sigma is going to be, since it's a diagonal matrix, it's just going to be the sigma squared.
Yeah.
And then you're left with this thing here.
Okay, so then basically we have V sigma squared, because V sigma is transpose E, sigma is squared. So V sigma squared V. And then we go down here, V sigma squared V transpose over N. Yeah. And then I see. Thank you. Okay, so again, what's happening here is we're exploiting singular value decomposition in order to efficiently compute our covariance matrix, which is, as you remember, is step 1. And then what we're going to do is we're going to, according to eigen decomposition definition, we need to get this eigenvectors of the covariance. And so I think what's happening here.
So I don't think it's saying that we need to get them. I think it's telling you that that's what they are.
That's what they are. You've already got the data. So
yeah. So as soon as you compute the singular values, you have. So you can do this in MATLAB. MATLAB will spit out U. It'll spit out sigma, and it'll spit out V.
Right.
And so this is just kind of rearranging things to show you that if you look at how this kind of shakes out and you multiply both sides by V, you'll see that this actually solves our problem. This V are going to be the principal directions that we care about, actually. So the vectors inside the matrix V are going to be our principal component direction.
Nice.
Yeah. It's basically all of the eigenvalue or eigenvectors that are ordered by magnitude of the original eigenvalues that we solved. So you're just constructing a matrix based on the lambdas that we ordered, like the eigenvalues that we ordered previously.
Okay. All right. So I think let me just talk about one more thing that I actually understand. The question is, are principal components good for classification? The answer is actually no. It's not. I think if you have and like the texts try and show this. I don't understand this very well yet, but because we're looking for the dimension with the largest variance, And assuming, information theory says the largest variance has the largest entropy, which carries the most information, is going to ignore small eigenvectors that don't have that capture that much variance. So if you have something like there's not a lot of variance in this direction, even though our classifier has blue on this side and red on this side. So PCA is going to ignore this direction in favor of this. So depending on your data set, it might not be that good for classification. So instead, what you would want to use, I think this is here. Nope. Wow, whatever. There's other ways to do, I guess, to reduce your features, I guess, to reduce the data. And I think this one's called like a linear decomposition, something analysis, which is a little better for classifying and like pulling out your largest features, most important features from your data set, as opposed to PCA, which will not do well if it's classified in a way like this. Does that make sense?
Yeah. Can you go to 40 so we can just read what that says? Okay, that doesn't really help very much. But I see what you're saying. I mean, that's not what you're basically saying that it's not trying to classify things. It's trying
Right.
to get you the most information, the most bang for your buck.
Exactly. So, yeah.
And those aren't necessarily correlated. Yeah, those aren't necessarily the same thing.
They're not the same thing. All right. In summary, PCA finds the orthonormal basis of the data, right? So you get like these unique features that are independent. Source dimensions in order of importance. So you're able to like determine, okay, well, what portions of, I guess, how much information within my data set is captured in order of importance. And then discards low significance dimensions. So you might take K amount of your D dimensions. It's good for getting low dimensional representations of your data. So if you need to do compression, you can do something like this because you get lower dimensions and it removes noise. So you don't really care about the lower dimensions. I guess the less information carrying subsets of data. It doesn't know class labels. So if you want to do dimension reduction with class labels, use a different algorithm. And it can only capture linear variations. So if we have nonlinear correlation, I guess, variations, might not be the move. So here's an example of using image compression, right? So there might be, depending on the, I guess, pixels. So let's say this is like 1,000 pixel picture. And then each pixel has like 3 RGB values. This is probably grayscale, but you can imagine like there's a lot of dimensions when you consider each pixel has like 3 options. Mm-hmm. And so how can we like capture the information of the image in as little, I guess as small as possible. So what you could do is you could use PCA and you say, I'm just going to take my 50 most important dimensions using PCA. And by doing that, you're able to reconstruct the image pretty well without having all those other information carrying dimensions that were less important. So what some people do is they'll have these different like measures of like, okay, well, how do I choose my order that I want? So in this case, they chose the 50 principal components. Some people say I want to capture 90% of the information. You might also, I think there's other ways to define it, but again, choosing the number is more of an art than it is a science. It's experimental, and I think it's highly dependent on the application as well. All right, that's principal component analysis. Should we start recording?
Oh, yeah.